So this is Physics 105, Chapter 16. It's superposition and standing waves. Superposition is a fancy word for interference, how waves interfere. And I want you to know this is something that we'll use in Physics 106. So chapters 15 and 16 we'll use in Physics 106. Objectives. We're going to understand the principle of superposition, which is interference, adding. Understand how standing waves are generated. That's a super big deal, standing waves. We'll talk about that when we do quantum physics in Physics 106. Calculate the allowed wavelengths and frequencies of standing waves on strings, transverse waves, and then sound waves, longitudinal. So it's going to be very different. Understand the difference between constructive and destructive interference, and how the interference between two sources produces a pattern of constructive and destructive interference. And then we're going to calculate something called the beat frequencies. That's if you have two sources with nearly equal frequencies. All right, so let's talk about this superposition, this interference. Okay, so here we have a wave pulse moving to the right. Here we have a wave pulse moving to the left. This is where they interfere. And then what do you notice? This guy looks the same as it did up there. This guy looks the same as it did up there, right? All right, so here's another example. All right, so here's where they interfere. And then, here's another example. All right, so what do you notice? What are these waves doing? Well, they're just passing through each other, right? I mean, look at this one here. And then look at it here. It's the same, right? That one is the same. So the waves are just passing through each other. Now, does that happen with particles? No. My hand didn't pass through the wall, right? All right, so as I told you in Chapter 15, I'm trying to help you believe that waves and particles are completely different, which is a lie. And we'll see that when we do quantum physics. All right? Okay. So this is called constructive interference. It just means that this pulse and this pulse, they add. But again, all they're really doing is passing through each other, right? All right, so constructive interference. Here's another constructive interference, right? So they just add, except now it's down, not up, right? But again, they're just passing through each other. So it's complete adding. So constructive interference is complete adding. On the other hand, let's have destructive interference. So here you have a up, here you have a down, right? And they interfere. And what do you notice? It looks like nothing, right? For that moment where they interfere, where they overlap, you see just a straight line. So that's called destructive interference. But again, nothing really was destroyed. This one just keeps moving its merry little way, and the same for this one. So they're just passing through each other. But when they interfere, it looks like they destroy each other. So this is called the principle of superposition. It's not a big deal. The total displacement or the net displacement is just the sum of the individual ones. That's all it is. Whoopee, right? So here you have one down and another down. You add them, you get two down. Whoopee, right? Here you have a positive and a negative, same shape and everything. And so when they interfere, you get a plus and a minus, you get zero, right? Zero. So that's all that is, okay? Just add the individual displacements. That's all it is. Here's another example. I really like this one. So you have this like triangle thing, and then this half a circle, and they're moving towards one another. So they closer, and then see how it's kind of weird, right? How they interfere. There's a circle and there's a triangle. Yeah, and then they just move past each other, right? They just move through each other. So I think that's pretty neat right there. All right, so let's see. Two identical pulses of opposite amplitude. So one's up, one's down. Travel along a stretched string and interfere destructively, like we already talked about. Which of the following is or are true? So pause your video and figure it out and get ready to vote or whatever. Okay, I assume that you figured out which is true and which is not. All right, so, I mean, we talked about this, right? There, that's what it is. Agree? That's so. All right, so number one is certainly true. There is an instant at which the string is completely straight. Totally true. Two, when the two pulses interfere, the energy of the pulses is momentarily zero. And that's insane. We learned some time ago that energy is conserved. It can't just go to zero, right? And also, I mean, remember, the waves are just passing through each other. So how could that be true if the energy went to zero? So 2 is wrong. 3, there's a point on the string that does not move up or down. Well, that's the same thing as 1. So there you go. So 1 and 3 are correct. All right, now we want to talk about standing waves. Again, this is a big deal, and we'll see it again next semester. And we'll start off with the easy examples, just transverse waves like rope. All right, so here we go. Let's see a little video.
What we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle's a node. So we have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump. Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 and 1/2 wavelengths. So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
All right, what do you notice? So initially, so hold it, let me draw something. So there was a string held between 2 points, and then there was a wave driver, created a wave, right? And so the wave traveled this way and then reflected. And at certain frequencies only, this standing wave was created. Only at certain frequencies. And so a standing wave, it's no longer traveling, right? So it's kind of interesting. You start off with a traveling wave, it reflects, and then as I said, at certain frequencies only, the traveling wave ceases to travel, and you get this standing wave. Okay? I just showed you that. All right. So 0 amplitude, always. 0 amplitude, always. 0 amplitude, always. Okay? And then this, you saw this on the high-speed camera. So this goes, it goes between the max and the min and everything in between. Okay? So this here does not oscillate, so it's called a node, N-O-D-E. That's kind of nice because it's easy to remember. Node, just think of no oscillation, right? So node, 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 no oscillation. This here, where it goes between the max and the min, is called an antinode. All right? That's supposed to be a plus or minus. Okay? Antinode, like the anti-Nephi-Lehis, right? Whatever. Okay? So the oscillation amplitude changes with position. Here it's always 0 at the node. At the antinode, it goes between max and min and everything in between. All right. Now, we want to talk about wave reflections and discontinuities. And we're going to see this again in Physics 106. Pay attention. All right. All right. So here's a situation where the rope is tied to a ring, and the ring can move up and down on the bar. So you have this. So it's a free end. Okay, a free end. So the wave comes in, the pulse comes in, and then it reflects. Agreed? Now what do you notice though? Here, the pulse was up, right? Up. And when it reflects, the pulse is up. Okay? So that's what you notice, okay? On the other hand, now let's take the rope and tie it to the wall or something like that. So you have the pulse is up, comes in, and what happens on the way out? It flips, right? It inverts. Okay? It inverts. So here's the big deal. Here, for the free end, the reflecting pulse is not inverted. For the fixed end, the reflecting pulse is inverted. That's important. Now, keep that in your head, and let's think of discontinuities. What's that mean? A discontinuity, it just means that the rope changes. So you have a different mu, which is the mass per length. Remember we had this on that formula for the velocity of a string wave? Okay, that mu is that mu. All right? So you can kind of see, here's this fat, this real high, big, fat rope, and here's this little wimpy rope, right? Okay, so here we're saying that the mass per unit length of this guy is greater than the mass per unit length of that guy, okay? So what's going to happen? What's going to happen? Well, so this wave pulse, when it gets this discontinuity, some of the wave is going to just keep going, but some of it is going to be reflected, all right? That's the important thing. So let me show you that. All right. So again, so see some of the pulse, so the pulse just kept going, but then some was reflected. Now here's something kind of interesting. Notice what it says. It says here, string with faster wave speed, and here it says string with lower or slower wave speed. So why is that? Well, it's just because of this, right? It's just because of this. I mean, over here, this mass per unit length is greater than on the right, so therefore the speed here is going to be less than here. Okay? But anyway, that's really not important for this. What's important here is where if the mass per unit length left is greater than the mass per unit length right, notice the pulse does not invert. Agree? Right? The pulse does not invert. Okay? Keep that in your head. Now, so what is that like? So there's no inversion. So that's kind of like this, right? It's kind of like having a rope with a free end. Okay? So if mu left is greater than mu right, there's no inversion. On the other hand, okay, so the reflected pulse is not inverted. On the other hand, look at this. So now we have mu left is less than mu right. So this is just a little piece of string. This is this big fat rope or something like that, right? And look what happens. Again, some of it travels through, some is reflected. But what happens? When mu here is less than mu there, the pulse is inverted. So the reflected pulse is inverted. Okay? And again, it's only true if the mass per unit length here is less than the mass per unit length there. All right. Now, and again, that's similar to this, right? To the fixed end. The reflecting pulse is inverted for the fixed end. Okay. Now, for a standing wave, again, you have a traveling wave and it's fixed, all right? So what happens? It's inverted, right? You have it coming back here, it gets inverted, okay? So there you go. All right, now we want to completely analyze these standing waves. So let's do it. All right, so as I said, and as the narrator said in that video, you only get standing waves at certain frequencies. So what we want to do, we want to find those frequencies. All right, that's what we're going to do. So here you go. So here's a nice picture, right? And the guy talked about this, right? So here's one wavelength, here's another wavelength, right? And so this is a half a wavelength, that's a half, half, half. All right. And so what does it say? It says the nodes and the antinodes are spaced a half a wavelength apart. Well, great. Okay, so let's say, so the first one that was shown on the video, I don't know, it was like this, right? So how much of a wavelength is that? Well, that's just this part, agree? So this is a half a wavelength. So let's say this is the length of the string, right? That's a half a wavelength. So here the length of the string is a half a wavelength. And then he said like the second possibility was this. I'm not a good artist, right? All right, so here you have 2 half wavelengths. I'm going to write it 2 half wavelengths. I'm not going to write it, you'll see why. All right, then the third possibility was like this. Okay, 1, 2, 3. So we have 3 half wavelengths. All right, so here we had 1 half wavelength, 2 half wavelengths, 3 half wavelengths, and you can keep going, right? All right, so basically, so here, you know, so okay, so this is equal to L, right? This is equal to, so 3 half wavelengths, so L equals that, right? So L is a half, here it's 2 halves, here it's 3 halves. So all I'm saying is the possible lengths of the string, we can just write it like that. Lambda over 2, 2 lambda over 2, 3 lambda over 2, and so forth and so on. Those are the possible string lengths. All right, now we're going to do something that you may have never seen before. I don't know. We're going to use what's called the index. So it's too much trouble to write that, right? So what we say, we're just going to say that the length of the string is m lambda over 2, where m is not the mass, it's the index. It stands for 1, 2, 3, on and on and on, right? Index, no units, just a number, index. Okay? Well, that's cool. All right, now we can write, let's solve for lambda. All right, let's just solve for lambda. So lambda equals 2L over m. It's probably a good idea to put a little subscript here for m. Okay? All right, so we have lambda m equals 2L over m. And again, m is the index. It can't be any mass, because what's mass with a wave, right? Doesn't make any sense. Okay, now remember, I said we want to find the frequencies that you get standing waves. Well, this is wavelength. Well, how do you get wavelength? I mean, how do you get frequencies from wavelengths? F equals ma, right? I know it's not F equals ma, but I always call this F equals ma for waves. Okay, so here you go. All right, so the wavelength is v over f. Okay, so that means that this equals v over f. Now we want to solve for f. So just look at this. So let's just flip it. So we have f over v equals m over 2L. Now we want to get f, so multiply both sides by v. And that kills that. Ta-da! All right, so let me write it again. So we have f equals m v over 2L. Now why did I pull it out of the parentheses? Here's why. Again, m equals 1, 2, 3, on and on and on. All right, so in the video, the guy talked about a fundamental frequency, right? Again, this is FM. Put a little subscript there, it helps. So the fundamental frequency, the lowest frequency, is just obtained by putting an m equals 1. So it's just v over 2L. And then F2 would just be twice that, right? 2 times v over 2L, which is just v over L. F3 would be 3 times that, and so forth and so on. So you noticed in the video, I mean, once he found the fundamental frequency, which is 8.5, it was simple to find the others, right? The second one was just twice that, the third one was 3 times that, so forth and so on. We can also write this like this. Fm equals m times F1. Yeah? So again, if you have find F1, piece of cake to find the other ones. Just multiply by 1, 2, 3, 4, 5, you know? All right, that's all there is to it. And that's a nice picture too, right? Better than mine. All right, so there's the equation. So you should know how to figure this equation out. I'm not going to give it to you on the exam sheet. You should be able to figure that out. All right? Okay, now let's talk about violins. All right? So here's the equation, m v over 2L, but what's v for a violin string? It's square root of tension over mu. So the fundamental frequency F1 is v over 2L, but what's v? It's this square root, right? This is the velocity for a string or a thin wire. So that's the fundamental frequency for a violin. That's all there is to it. Now, here's a question for you. That's just a fundamental, right? Then you have other ones too. But okay, so here's a violin. So, and let me write that equation down. So for a violin, so F1 equals 1 over 2L square root of tension over mu. And then, of course, Fm equals m times that. So m over 2L square root of tension over mu, right? So that's the frequencies for a violin. Now, in the real world, how do you get different sounds from a violin? I mean, it plays all sorts of different frequencies, right? Well, how do they do that? I mean, and think about it. The string lengths are the same, right? The string lengths are the same, and the tensions are nearly identical. I mean, if you had the tensions really, really different, you'd bust your violin. So the string lengths are the same, the tensions are almost exactly the same. So how do they get different frequencies? Well, look at the strings. The strings have different mass per unit length, right? They have different mass densities, different mu's. And then, the violinist can put his or her fingers in a different place and change the string length, right? So that's how you do it. Okay, here's something closer to home maybe. A microwave oven sets up standing waves, sets up a standing electromagnetic wave. We'll learn about that in Physics 106. With lambda equals 12.2 centimeters. So great about that. It's a wavelength that's strongly absorbed by water in food. I mean, think of food. Can you think about, there's not a whole lot of food that doesn't have water in it, right? So this is awesome. Okay, so you get the standing wave, 12.2 centimeters, a wavelength that's strongly absorbed by the water in the food. Okay, because the wave has nodes spaced half a wavelength, which is 6.1 centimeters apart, the food must be rotated while cooking. Otherwise, the portion that lies at a node where the wave amplitude is 0 will remain cold. Makes sense, right? Now, here's what's kind of, I think, very interesting. So obviously the people who designed the microwaves knew about this, right? I mean, they had to. But when the first microwaves came out, they didn't have the turntable. So what does that mean? It means it wasn't cooked evenly. So they sold those for like a couple of years or so, and then they finally decided to put a turntable in them. And I always thought to myself, why didn't they put the turntable in initially? They knew about this. And I thought, maybe it was a marketing thing, right? Force everybody to buy a new microwave. And I don't know. But anyway, kind of interesting. All right, so here is a question. So everybody read that, please, while I erase the board. All right, so this is a standing wave. It has a period of 8 milliseconds. So we want to draw snapshot graphs of the string every millisecond from 1 to 8. All right? Okay. Oh boy, I can't draw. Well, shouldn't say can't. So yeah, 1. Okay, so this is 1 millisecond, 0, sorry. Okay, I gotta get that 8. All right, so this is 0, this is 1, 2, 3, 4. Okay, so let's do it. All right, so I'm not an artist, so don't get too picky on me. Huh? All right, so that's what it looks like at t equals 0 milliseconds. So what's it going to look like at 8 milliseconds? Well, the period is 8 milliseconds. So if it looks like this at 0, what's it going to look like at 8? The same thing. So just pretend this is the same thing, all right? All right, same thing. Pretty awful, well, whatever. All right, now, let's see. So 0, 8. So what's it going to look like at 4 milliseconds? What's it going to look at a half a period? So I mean, think about it. Up, down, up. Up, down, up. So what's it going to look like at a half a period? It's going to be down, up, down, right? So at 4 milliseconds, it's going to be like this. Whatever. Okay? Right? Half a period. Okay. Now, what's it going to look like at 2? Now think about it. At 0, it's up, down, up. At 4, it's down, up, down. So what's it going to look like at 2, which is half of that, halfway between that? What's it going to look like? Well, it's going to look like this, right? Just straight, right? Straight. What's it going to look like at 6? So here, down, up, down, up, down, up. What's it going to look like at halfway between there? Just like that. Okay. What's it going to look like between? How about at 1? What's it going to look like between that and that? Well, it's going to be sort of like this. Again, don't be super picky. Right? Something like that. Here, it's going to be sort of kind of like this. All right? How about here? So now it's going from straight to that. So it's going to be sort of like this. Like that. And here, it's going from nothing to up, down, up. So it's going to be sort of like this. Yeah. Sort of, kind of. All right? I hope. Make sure you understand that. That's important. So here's a better one. Right? Yeah. Okay, so make sure you understand that. All right. This is a good place to quit.